Okay, so maybe we should make a start with our special year seminars in the second term. So it's a pleasure to have Salim Tayou speaking about modularity of special cycle. Wow.
Well, thanks, Jonathan, for the introduction, and thank the Institute for hosting me in this special year. It's great to be here. So the organizers asked me to give a series of 2 lectures on this topic. So the first one today, and the second one will be next Thursday, same time. And so the goal of my talk will be to describe the components of the Hodge locus more from in connection to theory of modular forms, and like how the generated series of the components of the Hodge locus more often than not form or give a modular form. So before I start talking about this geometric perspective, I wanted to just start slowly by talking a little bit about modular forms and how theta series of lattices give modular forms, and then talk about the geometric perspective and connect it to like variations of Hodge structures and modular forms. Please feel free to ask any questions at the time. Okay, so yeah, let's just start with some motivation and background. And let's fix a lattice which has a quadratic form Q, which is positive definite. So L is a lattice, which is isomorphic to z to the power n, so finite rank 3 z modules with a z module with a symmetric bilinear carrion or a quadratic form. And this quadratic form is positive definite. And one of the really classical questions that goes back to Jacobi and Siegel is if you have an integer m at least 1, how many ways can you write it as a value of quadratic form? So let's call this number here m. The number of ways you write m as a value of q. Okay, so this number by themselves, isolated, they are very hard to compute, but if you put them in a generated series, and this is the perspective really that adds or helps finding these numbers. So the theta series of this lattice is the sum over all the lambda in L of q to the power q lambda, which is the same thing as the sum over all n bigger than 1 of these numbers a of m, q to the power m, and q here is exponential of 2 pi I tau, and tau is in the Poincare upper half space. Okay, now the theorem here is that this generated series is a holomorphic. It's a holomorphic function, that's clear. The AM is easy to show. You grow most polynomial in M. It's an exponential factor. So this is the holomorphic function, but it also enjoys some invariance property under the action of SL2Z on this upper half space. So in fact, it is a modular form of weight n over 2, where n is the rank of the lattice, and level some congruent subgroup gamma in SL2Z. It's usually possible to find what's this congruent subgroup just from the intersection matrix of Q, but let me not do it here. Okay, so what those 2 terms mean simply is that if you have an element gamma in gamma that you write as A, B, C, D, then it acts on the Poincare upper half space for your fractional linear transformation, and the L A tau plus B divided by C tau plus B is equal to C tau plus B to the power n over 2 times theta L plus N. Okay, so why is this interesting? Well, for following reasons. First, if you just look at the so why is this interesting? If you look at the space of all holomorphic function on the upper half space that satisfy the same equivariance condition, so a basic holomorphic modular form of weight n over 2 with respect to the gamma, this is a finite dimensional vector space. And we have other ways of producing elements in this finite dimensional vector space via the theory of Eisenstein series. So you know that theta L is an element of this space, and then you can produce enough Eisenstein series to fill all the possible dimensions. Then you can write a linear combination of theta L in terms of those elements, and then identify the coefficients and get closed formulas for the number of ways you can represent n as value of q. So let's do an example. So a simple example, like just L, which is squared, and q is the xy is x squared plus y squared. And now this a on n is just the number of ways you can write n is a sum of two squares. Yes, this is the classical example. the theta series in this example is simply the sum over all AB in z squared of q to the power a squared plus b squared, which is just the square of another theta series where u of tau is the same thing, where you're only summing over z. Okay, so if you take the square of this function, you get this function. Now, it's easy to see that, or relatively easy to see that this function u is invariant by translation by 1, and that nu of minus 1 over tau is I tau to the power 1/2 times nu of which or just my numbers. Sorry, minus 2 I tau to the power 1/2. So, okay, so this is easy just because this Q is already one periodic, and this is just Poisson summation formula, which is really the magic formula for obtaining all the modularity theorems that I know. Okay, so from this two relationship, you get that theta L of tau plus 1 is equal to theta L of tau, and that theta L of minus 1 over 4 tau is minus 2 I tau times theta L of tau. Okay, so it turns out that just having these two relations is enough to conclude that theta L is a modular form of weight 1 with respect to gamma 1 and 4, simply because these true transformations generate this group. In fact, the dimension of this space of modular forms is 1 also. So if we can produce one other element in this space, then we can completely compute this number of ways of representing M as a sum of its squared. And it turns out that this is where the theory of Eisenstein series is helpful. like another way, like theory of Eisenstein series, give us another element, d1 of chi, which is 1 plus 4 sum over n bigger than 1, then the sum over all the divisor of n of chi of d, q to the power n, where chi is the non-trivial character mode 4, the unique non-trivial character. And so by comparing the constant terms, because the space is dimension 1, you get that theta of L is equal to d1 of chi, and so therefore an is equal to the sum of the divisors n, or 4 times the sum of the divisor n. Okay, so this is an example of how one uses modular forms to enumerative problems. Okay, now more generally, theta series of positive definite lattices allow also to construct Siegel modular forms for basically any G in the following way. If you can also get Siegel modular forms. So if you fix a G at least 1, so you can consider the theta series. Theta of tau, where now tau is an element of the Siegel upper half space. These are matrices x plus ay, which are symmetric, and y is positive definite. And this is defined as the sum over all g vectors in the lattice L of q to the power. Okay, so I will write it to the power of a matrix. That'll say exactly what I mean. So I take the intersection matrix of these vectors with respect to the pairing, and q to the power of a matrix is simply exponential of 2 pi I trace tau times the matrix. Tau is a matrix, m is a matrix. This is exponential 2 pi I tau times this intersection matrix, which you can also rewrite as the sum for all the matrices that are semi-positive definite of the number of ways you can embed a lattice of like a g-dimensional, if M is positive definite, a g-dimensional lattice with intersection matrix M inside L. And this is what this number is counting here, Q to the N. So this gives, if you can find Eisenstein series in the space of modular, I guess what's the theorem here? This is also a holomorphic Siegel modular form of weight n of 2 and some level gamma inside the symplectic group sp2gc. So the theta series of lattices, I guess the takeaway is that theta series of lattices produces modular forms and Siegel modular forms. And you know other examples, then other examples of modular forms, even in those spaces, you can get closed formulas for number of representations or number of embeddings of a lattice in another lattice, and these kind of problems. Okay. Are there any questions? Now, what if the lattice is not positive definite anymore? Obviously, like all this sums that I've written become meaningless just because you will have infinitely many points with a given norm. So this number here will be infinite. There's not going to be a convergence. There's going to be a convergence issue. And so there's a way to fix this, like using non-holomorphic theta series, but the point of view I would like to adopt goes in the direction of the special here is how we can produce modular forms geometrically using variation of Hodge structures. Okay, so now the setting is, so let's S over C be a smooth connected complex algebraic variety. And consider a polarized variation of Hodge structure of weight 2 over S. Weight 2 over S. Okay, so what is this? What is this data? So this is the polarized variation of Hodge structure over S. This is the data of a local system, a holomorphic, like a filtration by holomorphic subbundle on the plot bundle associated with this local system. S. So polarized means that there is a quadratic form, a flat quadratic form of this local system. And then this data is subject to some conditions, meaning that for every point S in S, if you take the fibers of all this, the local system of this filtration, you get a pure Hodge structure of weight 2. So plus some conditions, which are for every S in S, like this PZ of S, then the fiber of this filtration and this quadratic form is a polarized Hodge structure of weight 2. And a Griffith's or Griffith's transversality condition. Which is that so this flat bundle has a connection. So sections are exactly like complexified. And the way this connection shifts this filtration is by at most 1. In a lot of the examples that we'll see today, this condition will be automatic, but in this general weight 2 condition. Okay. I'm focusing on the weight 2 because this is where interesting examples happen. If you're doing higher weights, then recent work of Greg and Emmanuel and Bruno shows that we're not going to have like anyway a lot of Hodge loci. So this is like really one of the interesting cases to do. Okay. Now the Hodge locus of this variation. In fact, I will mostly focus on the Noether-Lefschetz locus. So this is basically just the locus of points S in S, where if I look at VZ intersected with F1, so this is the group of Hodge classes, and this group contains more elements than for a very general S in S. Okay, so I mean, one example maybe to keep in mind for where this if you have not seen this before, for where these variations come from, is the following. If you start with a family X over S of smooth projective morphism, Let's call this morphism. Then the cohomology of the fibers, in fact, form a local system just because locally over small open sets you can trivialize them in a C infinity way. So the R2 at lower star Z, let's say modular token, is a local system on S. So this is an example of this VZ. And then the filtration and the vector bundle will come from the relative sheaf, or the relative complex of the round bundles, and like the R2 F levels out of this complex with its differential. And so this will be the V, and then the naive or stupid filtration of this complex gives this, like when you take the cohomology, like the derived cohomology of this filtration, you get this filtration on F0V. In fact, the fibers will just be the hot structures on the fiber of this morphism. That's what you get when you do this operation. Okay. Now, let's get back to this noted Lefschetz locus. So this noted Lefschetz locus is a countable union of algebraic subvarieties. I guess since we're doing weight 2 case here, and we have Lefschetz 1-1, this is just a Hilbert-Scheme type argument. I mean, the more general results where you consider any weight as a deep result of Dulin, Catani, Kaplan, and has been reproved also recently using omnimality by like Baker, Bruno, Winkler, and Jacob Zimmerman. Yeah, in this case, it's mostly Hilbert-Scheme arguments. Okay. Now, this countable union of algebraic subvarieties, there's a very nice way we can package them in a generated series, namely in the following way. The fiber, so if we just fix a point in S1 for all, the fiber of this local system at S and along with its quadratic form will be isomorphic to a free Z module, so a lattice with a quadratic form Q, and the signature of this quadratic form will be the form P comma 2Q, where Q is the rank of the vector bundle F2, and P is the rank of F1 mod F2. So in other words, these hot structures will all have Hodge numbers Q comma P comma Q. What would that be from 1 2? Now, now I define Zm to be all the points in S for which there exists a lambda in this like group of Hodge classes whose value under Q is equal to M. Okay, so in fact, this is just an algebraic subvariety of S, and the noted Lefschetz locus that I defined above is just the union over all these schemes. I should say immediately that I'm assuming that this local system has no fixed part, but so meaning there are no elements here that are Hodge classes everywhere, even after finding some finite base change of S. Okay, so we just maybe not just too much. Okay. Now, the generated series I would like to consider is the sum the sum over all n bigger than 1 of z of n q to the power n. And I can look at this generating series in the Chow group of S, of cycles of let me change the P and Q here and call them A and B, okay, just to avoid conflating them with the Q of the variable here. So this is A comma to B. And so the B is the rank of F2 and A is the rank of F1 mod F2. So the Hodge numbers are B comma A comma B. Okay. So the cycles typically will have codimension B, right? So to be for a lambda to be a Hodge class, it has to be 0 in F0 mod F1, and that's the holomorphic vector bundle of rank Q. So there's the Q holomorphic conditions. Of course, there might be some exceptional components of smaller codimension that I will ignore completely because I'm just going to be taking the classes of codimension B. And for the constant term, I will consider the top churn class of the dual of F2. Okay. And this is now a generating series with coefficients in the Chow group of S.
That's not Q.
Sorry, what? C, yes, thanks. Yeah, C. Thanks. Yeah. This is the top chain class of the F2 dual. All right. So now, I think these will be the guiding questions for the series of two talks. I mean, this is really Kudla's program, and it's originated from papers of Helterbrook and Zagier and Kudla and Millson. And so question one is theta a holomorphic modular form? Well, I mean, it turns out that in general, asking something to be a modular form in Chow is a very hard question. So instead of looking at these classes in Chow, you can look at them in cohomology. How about?
Can I ask a very simple question?
Yes.
What is B?
B?
Yeah.
The rank of F2.
B is the rank of 2. Okay. And
Yes.
so B is.
So yeah,
Oh,
I see. Could I mention B cycles
Gotcha.
in S, where you would expect that these cycles live?
Thank you.
Okay, so now if you can't prove them in they're modular in Chow, how about in cohomology? H2BS with the coefficients, which in general is a little bit easier. Okay, so this is question one. Now question two is suppose that you can prove that there are modular forms, then let's say S is a curve. If it's not compact, then usually you cannot extract any enumerative geometry information. You cannot take degrees of zero cycles on a non-compact curve. So you don't get really any meaningful information. And so it's like really deep to Kudla is is there a compactification of S where like suppose that now is there a compactification of S where this theta is now instead of taking you take the Zariski closure of the cycle, this algebraic subvariety, you take a compactification, you take the Zariski closure, and you assume also that the F2 dual, let's say, extent in some way, like the Hodge bond will extend in some way. So with this extension, we call it denoted with a bar. It's still a modular form, or if it's not a modular form, maybe it's gonna be holomorphic. So we can also allow non-holomorphic modular forms, and this is typically what's gonna happen. And the final question I'm not gonna talk at all about in this two lectures, which is the arithmetic story. S, for example, was defined over a spec of OK for a number field. And all these cycles, suppose you can descend them to also to this number field in some way. Then can you, for example, enhance them to arithmetic cycles, like define currents on them? These are part of the arithmetic Chow group of this S. And for these new cycles, call them Z hat M, the generated series is a modular form in some way.
Sorry for question 2.
Yes.
How can it be non-holomorphic if it has a Fourier expansion with constant coefficient?
Right. So that's a very good question. We'll see in examples like it's going to be holomorphic, but maybe it's not gonna transform under SL2Z in the right way, and you have to add something non-holomorphic to make it transform in the right way under SL2Z or a subgroup of SL2Z. And the examples to think about, and we're going to see how we'll have time to do it today, is E2, 1 minus 24, sum over n bigger than 1 of sigma 1 of n q to the n. So this is a holomorphic function, which does not transform well under SL2Z, but if you add to it like 3 minus pi y, maybe plus 3 pi y, then it becomes non-holomorphic and transforms well under SL2Z. This is typically what's going to happen. Thank you. Yeah.
So do we not expect question 1 to be true all the time?
Question 1?
Yeah. Is it not supposed to always be a
Yes, it is going to be true. Yeah.
So question 2 should sort of, like if that were known, that question 2 would not be. Like every extension, every compactification should give you something.
So, well, I mean, a compactification will add, you will add more cycles. So it's a very different question. In fact, sometimes in question 1, the modular form you get will be just a zero modular form. But then when you compactify, this is where the cycles have actually non-zero homology classes. Yeah.
Can you formulate and maybe prove question 1, at least in some cases, on the period domain?
It's exactly what I'm going to do. Yes, thanks for the question.
And so another question.
Yeah.
A connection between this picture and the picture you were sketching out in the first case. Is it this visualization, like just a lattice? No, I think right.
So is there a relation between what?
Between this picture and the one in the beginning, where you just have the lattice and the quadratic.
Yes, because in the next picture I'm going to say where you read, like when you talk about the period domains and the symmetric space, in the positive definite case, it's just going to be trivial symmetric space, just a point, and the cycles will be exactly the Theta series from the beginning. But when it's not trick, when there's actual geometry, there's going to be actual cycles. Okay, so now how do we approach all this question? In fact, the theorem, the first question, the answer is yes, at least in cohomology. In Chow, in some cases, but in cohomology, this is really a seminal theorem of Kudla and Millson from the 80s. And so how to do it somehow in a universal way is using period maps. Okay, so if you think about the space of all all the possible hot structures on on LQ that have Hodge number A to B and that's polarized by Q. These are a subset of a Grassmannian. So these are the W, which is a B-dimensional subspace of the complexification of L, such that the restriction of the quadratic form to W is isotropic, and there's a positivity condition, namely that Q of x bar is positive whenever, negative, so a negativity condition, whenever x is in W minus 0. So this period domain D, like how if you have a W here, you can take it W bar, and then you can take the orthogonal to W plus W bar, and this will determine a Hodge decomposition on LC. So this is the 2-0 part, the 0-2 part, and this is the 1-1 part. This is how you get all the way to Hodge structures on L. And now the you get a period map from, well, first if you consider the universal cover of S, where you can trivialize the local system just to the trivial local system L, then any point in S will define a WS in D, which would correspond simply to the fiber of F2 at S. So this is a B-dimensional space that defines its structure. Moreover, the local system determines a representation of the pi1 of S into this local system determines a representation of the pi1 of S into some subgroup gamma in the orthogonal group of L, so the arithmetic, like the orthogonal elements that preserve L. And this action here intertwine the action of the pi1 here, the action of gamma here. So the orthogonal group of the lattice acts on this period domain just by taking a subspace and move it to another subspace, and it will still satisfy the same conditions. And so this descends to a map from S to D of gamma, and this is the homomorphic period map. Now, the useful observation here is that all this limited Lefschetz locus will be just pullback of sub quotients of period domains from this D mod gamma to S. And the way to define them is very simple. For any n bigger than 1, well, I can look at, let's say if you have an element lambda in N whose value by Q is n, I can look at d lambda, which are just a set of B subspaces of D, such that lambda is orthogonal to W. So these are exactly the subset of Hodge structure where lambda is a Hodge class, right? Saying that lambda is orthogonal to W means it's also orthogonal to W bar, and therefore it lives in the 1-1 part, but it's also integral, so it's not an integral. I guess I used it to say it's also in W bar. But okay, now I can take the union over all such d lambdas for Q lambda is equal to n. This is a similar packaging that we did in the positive definite case, except now I'm packaging subvarieties of D. So this is a complex submanifold of codimension D. And the union over all of this d lambda admits an action of gamma. So this is what I call Zn. So this is a complex submanifold of D mod gamma. Okay, so maybe call it differently than the Zn here, but it turns out that the Zn here is just the pullback of this Zn here under the period map. So to avoid to simplify notations that usually we just call it Zn. So the pullback of Zm under the period map phi is equal to Zm from the Blackboard before.
And if you're in like some degenerate case where in Z, for M in particular on S, Zm is higher dimension than expected, I assume you define it still in this way. In Chow, you define it to be the pullback of the cycle.
Yeah, so I think for this to make to be clean, I should maybe say that S satisfies infinitesimal Torelli. Is that why you
No, it can satisfy Torelli, period, and still Zm can be a bigger dimension than expected, right?
Oh yes, those I throw away. So all the components that are bigger dimension, I throw away. Only keep the ones that they can put in.
And that's equivalent to pulling this back in this setting. You sort of, that's what it ends up being in Chow.
Well, okay. So when I pull back this, you mean I might have some like extra components that don't live in the right dimension.
That's right.
And then when I take that class in Chow, so those like I focus only on Chow Q, then those in the right dimension will disappear.
Oh, is that right?
Well, I mean, if they don't live in the right dimension, like the class in Chow will not be well defined, right? So like in Chow Q, like if I have something which isn't.
I'm not sure exactly how it works. I thought there was some way to do it with, like the Fulton's type machine. But
so I will do that when I'm doing matrices.
Right.
Well, I will cup them with like basically with the Euler class. Yeah, you're right. Okay. But yeah, somehow only the theory works a little bit the typical of this.
Mm-hmm.
Other questions? Okay, and so now the theorem. Okay, I guess I should say the F2, the F2 on D mod gamma, in fact, coincides just with the tautological bundle on D mod gamma coming from the Grassmannian. So this like is inside the Grassmannian of G of B-dimensional spaces on LC, like I guess the D. So there's a tautological bundle of L, which fiber is just the space W. So F2, in fact, is just the pullback of L, which is the tautological vector bundle. On this, or D mod. Okay, now D mod gamma in general will not have an algebraic structure, right? Unless B is equal to 1, will not be algebraic. So the most general theorem will be only true for this classes in cohomology, and this is what Kudla and Millson proved in the 80s. Is that if you take the Chern, the top Chern class of L dual plus the sum over all m bigger than 1 of the cohomology classes of these ZMs, q to the power m, inside the H2 of D mod gamma with R coefficients, this is a holomorphic modular form of weight 1. So, what would my number? A to B, A plus 2B over 2. And the level, some level, gamma inside SL2C. Okay, so this is like somehow like a universal theorem. Like now, every time you have a variation of Hodge structure of weight 2 over a base, you get a period map, you pull back this modular form, you automatically get a modularity theorem in cohomology. Of course, it does not help you at all with modularity theorem in Chow on the base of the variation of Hodge structure, just because this is a theorem in cohomology. Maybe there's an all minimal version of this.
Sorry, two annoying questions. One is
Yes.
like, what is the H there? You have two Q's, so what,
Oh, H2
it's like the A.
to B.
Yeah, okay, great.
It's to B, yes. B is always the rank of F2. Yes.
And I'm wondering, is this theorem, does it relate to the stuff you were showing us earlier with the more classical, like is it ultimately derived from do a bunch of the theta function stuff and then some upgrades here? It is, okay.
So the punchline here is that what Kudla and Millson do is that they construct this Kudla and Millson form, which is like some special form like that you could say is like the exponential in the usual theta series story, which has some invariance property under Fourier transform and which represents the cohomology class of this ZM. So they lift it to the level of differential forms. And then there it's just a theta series applied to a specific differential form, and then you use all the machinery of Poisson summation to prove modularity. Okay, now the interesting situation is when B is equal to 1. And in this case, the D mod gammas are algebraic varieties. And these are in fact, they're orthogonal Shimura varieties. And in fact, then in this case, we have a stronger version of this theorem. The original for divisors, it was so for this equal one, we are doing H2. So it's orchards. Then the C1 of L dual plus the sum over M bigger than 1 Zm Q to the M in the Picard group of D mod gamma. This is a modular form of weight, same weight and level. Correct. So it's an enhancement of this statement to the level of Picard, char1. Okay. So let me just do some examples. The case where B is equal to 1 is really interesting because it's the Shimura variety in this case parameterizes like K3 surfaces, at least when A is not less than 19. So if you have, let's say, X over S, a family of K3 surfaces, and okay, for the example, we'll assume that S is a curve, and it is also compact. Okay. So the relative cohomology of this family defines a variation of Hodge structure on S, and you get a period map from S to a certain B mod gamma, where the lattice here L and Q are the primitive cohomology of the family. And so, in fact, if you apply the theorem, you get that the volume, or like minus the volume of S with respect to F2, it turns out that this F2 is an ample line bundle on S. Let me just say 9 as a trivial. And that the sum over all m bigger than 1 of the degrees of this like elements of the northern lattice. Of course, this is going to be a modular form of weight. Is a modular form of weight 2. Where I guess this primitive cohomology will have some rank a comma 2. And so it's going to be 1 plus a over 2. And some level gamma inside S2Z. And so, for example, if you consider families of K3s where this lattice LQ is unimodular, and in fact, this will happen exactly in the following cases where the signature is 18 comma 2 or 10 comma 2 or 2 comma 2. Then the modular form that you get here will have, because of the unimodularity property, it will be level, weight 10 and level SL2Z. In fact, there is a unique one with E10. Well, it's rather E4 times E6. The two Eisenstein series of weight 4 and weight 6. So that's what's going to be the generator series. If you're doing weight 6 and SL2Z, there's also a unique one up to scalar, and it's E6, the one that's normalized. And then if you do 2 comma 2, you get something of weight 2 for SL2Z, and there are none. It just means that there are now compact families of K3s whose primitive cohomology is a lattice of signature Q2, which is unimodular. Okay, so that's I guess how you prove that such families do not exist. Okay, so now let's focus on this last example. And this will be the transition to question 2. So any family of K3 surfaces with a primitive cohomology of lattice of signature 2, which is unimodular, has to have some singularities somewhere. In fact, if LQ is unimodular of signature 2 comma 2, in fact, there are not that many. It's necessarily the sum of 2 hyperbolic planes. And the Shimura variety, the d mod gamma in this case, is simply the product of 2 modular curves. This is one of those exceptional isomorphism between O2 comma 2 and I guess maybe I'll cover O2 comma 2 and SL2 cross SL2. And so this has a compactification into compactify just each modular curve separately. And the ZMs in this dictionary are simply the Heike correspondences. So from a geometric perspective, like on this Y1 cross Y1, the universal family is product of 2 elliptic curves. If you want to understand it from the K3 case, you just take the Kummer associated to this product of 2 elliptic curves. And now this generating series here, if I call it Kudla and Millson. So this is an exercise. In this compactification, well, we have here, this is just isomorphic to P1, the coord spaces to P1 cross P1. So there is a line bundle, which is O11. And this Kudla-Millson form turns out to be just the Eisenstein series E2 times O11. I think there's a 1/12, minus 1/12. Yeah, minus 1/12, sorry. Yeah, it makes sense. Minus 1 over 12. Because I not a little bit too. Okay, I mean, what is this? This is just minus 1 over 12. 011 minus 24, the sum over all n bigger than 1, sigma 1 n times this long bundle 011 q to the power n. Okay, and this is saying the Picard group of P1 cross P1, double bracket H2. Okay, what this means is that all the cycles are just proportional to 011, which we know using the Haeckel polynomials. Like all these Haeckel correspondences are defined using this Haeckel polynomial, which have this B degree exactly this sigma 1 of n. And the Hodge bundle of y1 cross y1 coming from the elliptic curves coincide with 1 over 12 of 011, like just the line bundle 011. That's because the existence of the delta, which is a section of L to the power 12. Okay, so the summary is that this Kudla and Millson form is not it's not a modular form in this compactification. In fact, if you don't take the compactification in y1 cross y1, the cohomology class of this of the generalizing series is just 0 because y1 cross y1, this is just like a1 cross a1. There's a trivial Picard, and so the theorem just gives you like 0 is a modular form. That's great, but it's not very interesting. So you have to take this compactification to get like a non-interesting information. And I guess this is what question 2 is about. So to finish this point, if you we know that if you define E2 star to be E2 minus 3 over 4 pi y, then this now is non-holomorphic. It's an automorphic form and transforms like a modular form of weight 2. And so you can do the same correction to Kudla-Millson form. You can take theta kn. So you just have to do the right coefficients plus 1 over 4 pi y 011. This correction is a non-holomorphic modular form of weight. Okay, based on this example, Kudla conjecture that you can do that for any d mod gamma for divisors. So for any d mod gamma, there exists a compactification such that when you take the Zariski closures of this Zn, then there's some way, and conjecture is not really precise, but it just says there's some ways to correct them by boundary divisors. I mean, in this case, this 011 is, you can really like represent a class of something at infinity, like infinity, for example, that's P1 plus P1 times infinity. So there's some way to correct them by boundary divisors such that if I call this new cycle here z tilde m, the generating series of z tilde m q to the power n is okay, so there are many ways to formulate it. Maybe in the spirit of this question, I will just say it's a non-holomorphic modular form of the same weight and level. Okay, so this is what we prove.
This is only for orthogonal Shimura variety, yes? Because you need dividers.
So far, yes. Yeah, always orthogonal choice, yes. So this is the theorem that I will discuss next time. And this is joint work with Philip Engel, and so I agree with myself, 23, is that this conjecture is true. So next time I will do another example where just with the modular curve, like what happens also when you do the Kudla and Millson generator series just for the modular curve, and then explain this general statement for any orthogonal Shimura writing. So let me just stop here. Thank you.
Any questions?
I have a question.
Yes.
So you can sort of name these things. Are these almost holomorphic, like almost modular forms in the same world? Like what Zagier works on and stuff, or
Yeah.
are they actually different? It is the same.
It's well, I mean, so you have like a function that transforms like a modular form, like this relation. And in fact, they are the non-holomorphic is really like the really mild here. You don't E2 and you're just
Right.
subtracting 3 over pi y. So this is what's called quasi-modular forms.
Okay. So
Yeah. This is example, we really just get the quasi-modular forms. And the other example of the modular curve, we will get those other kind of examples that are called mock modular forms. But in essence, they're also non-holomorphic modular forms that transform in the same way. So these are all like automorphic functions. Some of them are holomorphic, some of them are non-holomorphic. I guess the terminology of quasi-modular or mock modular depends on.
That's the word. Yes.
Yeah. Depends on like how you correct, how much. I shouldn't say junk, like how much like.
How scary
Right.
Mock allows more.
Mock allows more junk. Yes.
The shadow, right?
There's a shadow. Yes. There's a whole. Yes. I mean, I prefer to think about them just as they're all like automorphic functions. Some of them happen to be homomorphic, some are non-holomorphic. But they're of course different ways to think about it.
There's supposed to be a principled way to find the boundary divisors you have to correct by.
I'm sorry, what?
Is there a principled way to find the boundary divisors you have to correct by?
Like what? How do we find them? Yeah. Oh, okay. Yeah, we'll see. Like in fact, for example, for this D mod gamma, there are natural compactifications, which are the toroidal compactifications, and their boundary divisors are like have very nice interpretations in terms of mixed Hodge structures, and those mixed Hodge structures naturally give you a Theta series that we saw at the very beginning, and that's the construction are actually very natural.
I'm just saying misunderstood something slightly, but this correction thing is not supposed to be true for arbitrary s. Like if we just have.
So, in fact, if you do it in this general setting, then arbitrary S, if you choose the compactification compatibly, like in terms of monodromy operators and things like that, then you can just pull it back to S. But if the variation is non-classical, like then this is what you have to somehow analyze directly on S. And I don't think that's been done so often.
Why is the turn class correct thing to do for the constant term?
Oh yeah, that's a very good question actually, and I think in the original papers of Kudla and Millson and Borcher, there's not a really good explanation for it. It's just like they declare it to be the case. The nicest explanation I found is by a paper by Kirti Madapuzzi, who just explains that this Chern class is in fact just a degenerate case when lambda is equal to 0. And then this is just like the normal bundle of the cycles in the universal cover are just like this L. And so if you do, I mean, he has like this whole using the algebraic geometry where the cycles just pop up naturally, actually. Like just from his formalism, the constant term has to be this one. And also, I didn't talk about Siegel modular forms, but also those corrections, the cup product with this CQ of L will appear naturally from his perspective, which I find the most satisfactory. Yeah, his paper is in archive.
Other questions? Otherwise, thank you very much.